Hello, everybody. This is our last topic on trees, and basically our last topic for this course. So, we talked last time about spanning trees, and so this was had to do with you had a graph. Let me start with drawing some random graph here. I make it a little bit bigger that we have enough things. So we have like this, say. Okay, so I have quite a few edges. So let's perhaps first verify that this is clearly not a tree because there's a lot of circuits, right? And another way to see this is there are far more edges than there are vertices, and there should be one less. Okay, so we are dealing here with a graph in general, and then we talked about the spanning tree. That was a tree that made up of edges of the original graph so that every vertex appears in that tree. And that's what a spanning tree is. But we have seen that graphs, as a tool to encode information in its plain form, in the most simple form, we have the information that it encodes is that there is a connection between two vertices, or there is no connection between the two vertices. That's the information that we can store in every graph. But there are graphs that we call weighted graphs. We have talked about these weighted graphs. These are graphs where every edge has a weight. It's not the name of the edge, it is the weight, the cost. Sometimes we think of it as cost, sometimes we think of it as weight, depending a little bit on the situation. So weighted graphs, although that's perhaps sometimes what people in mathematicians would prefer the word weight, but I'm going to use more the word cost because often this is what it's about. So imagine that this is a network of servers, computers. And now we designate one as, say, the main server here. And we have discussed this. The reason that we, for instance, would like to have a spanning tree in this situation is that we want to propagate an information from one server. Let's call this here the mother server, or which we then would like to be the root, of course. So this is the proposed root of our tree, and we want to propagate a message to all every computer has to get this message, but we want to do this most efficiently by saying, okay, the root says I'm going to send it to a couple of bunch of to all my neighbors or whoever the tree is. I'm going to send it to my children, and those children send it to their children. So we hand it through by generation, so that I don't have to send to everybody, right? This is like when something happens in the family, grandfather calls up his children and says, okay, this happened here, but I don't want to call everybody, so please tell your children that this has happened. And then their children have perhaps also already children, so he's a great grandfather, and they call them. So it's a kind of same situation. It's a tree that we built in this way. So that's a reason why in such a network of computers one would want a spanning tree. But now, it might be also that there's a cost involved, right? That one has to transmit these things via a line, an optic line or whatever, fiber line, whatever means we use. And those things are normally not owned by a company, but they are leased. So they have to pay a certain lease fee for it. And so just making up some numbers, suppose this is 10, this one is 12, this is 5, this is 4, this is 13. I'm just putting numbers here. I'm not really paying attention to what their numbers are, so just make sure that everybody has a number. 8, let's make this an expensive one, 18, and make this cheap, 2, and this is 5. Okay, so now the same question comes, and it is, okay, now that we have seen there are many spanning trees. In fact, we have several algorithms to make the first algorithm that we had was basically destroying circuits. right? Getting rid of circuits. But there are other ways of doing it that we have discussed, and that's for previous session. So I don't want to go over those anymore. We're not going to use those, like depth first and height, depth first and width first. No, depth first and I get myself. Breadth first and depth first. Sorry, I got a little bit. The names are sometimes a little bit confusing to me. Okay, right. So, but now this will provide just a spanning tree, but that necessarily is not the one. What we of course we want to do is reduce the cost, make it sure that it is as cheap as possible, and so we start with a root. This is now the question. Should we start with a root, what we normally did in the spanning trees? In this case, we're going to start differently. And so what we will do is, yeah, so I need to give names to things here. Yeah, let me do this. I'm going to have to name names here. So A, B, C, D, E, F, G, H, I, J, and K. Everyone. So this is not a vertex, right? It was just a crossing over. Okay, so right. So now I can talk about vertices, edges by listing the two endpoints of the vertex. Okay, and so the first algorithm is known as Prim's algorithm. So Prim's algorithm. Prim is a Czech mathematician. It's actually, if one realizes afterwards that it actually was discovered prior to him by a person, also Czech, called Jarnik. Sorry, I might not pronounce him correctly. Oh, sorry, Prim actually is not. I said that wrong. Prim is a Texan. It's Jarnik is Czech, and so this algorithm is rather simple. So what you do is you say, okay, I'm going to minimize both algorithms. There are two algorithms I'll discuss. Both algorithms are greedy algorithms, which remember what greedy is a little bit imprecise term, but it kind of reflects a certain methodology in your algorithm, namely that you're always going to try in your next step to do the best thing you can do in that next step, and then hope by that will result into actually the optimal solution. Now I'm going to present it to you, but I'm not going to prove that this is actually the optimal solution that you can read in the textbook. Okay, so what we do is we pick edge of lowest cost. Okay, so we're going to have to keep track of this. Okay, so I'm going to make here a table here. So here will be the edges that I'm choosing, and here will be the cost. And then I will have to add up the whole cost. Okay, so pick edge of lowest cost. Now, in this particular case, there are actually two. So we have a choice here, but you can either do it randomly, or you can have say, okay, let's go alphabetically first. So I'm going to pick AB here. So the edge AB. So remember, an edge is actually can be represented as a pair of two of its endpoints. And so the cost of that is 2. Okay, so I'm now coloring that so that I remember that this is my part of my tree. So what is the next thing? Well, you say, I want to take again the cheapest, but in this particular thing, we are trying to build the tree from where we are. So we have two endpoints, A and B. By the way, we don't know yet what the root is. I'll talk about how this becomes a tree yet. This is I said differently, right? We're not deciding what the root is. We're not looking at this from the perspective of vertices. We're looking at the perspective of edges, because those are the ones that have cost. So now my next thing to do is pick edge of lowest cost and adjacent to previous. edges. So I'm adding a little bit. So the first time we just picked one, but now we have to pick the next of lowest cost, which is adjacent to the previous edge. Yeah, because which. So I'm sorry. This is one sentence. Pick edge of lowest cost, which is adjacent to previous edges. So in other words, what are my choices here? I have only this guy or this guy, and the lowest one is 5. So I'm picking that one. So that would be AH. That has cost 5, so I mark this. Okay, and we keep doing this. What are our options now? Well, our options increase, right? We have 13, we have 6, and we have 7. So the best choice is 6. So I'm going to take 6. That is HI. That is 6. Okay, what are my options now? Oh, I haven't given a value to this guy, so that was wrong here. Sorry, I should have given a value to this one. Let me think what I want to do here. Let me give this 12. Okay, so we keep going. What are our options? We have more and more. Well, yes, more and more, right? So we have this. There's nothing here anymore, but this one, we have this edge, 13, we have 7, and we have 12. So we have to look, it's not just the endpoints of this path that we look at every point on the path where is the lowest edge possible. Okay, so what is in this case, that was, what was the value? 7 that we found, right? The other one, 13 and 12, no. So we take 7, okay. So here you see that it actually starts looking a little bit like a tree, right? So this was HJ. The order in which you list your vertices, HJ or JH, is not important here. So that was 7. Okay, what are our options now? Let's look. Our options are, we still have this 13, we still have this 12, and now we have 2 more, 5 and 8. So I'm going to have to take 5. That's the lowest available, so I'm taking 5. Okay, so we have now JD, and that has cost 5. Okay, what are my options next? Well, this D gives me extra option 10 and 12 and 4, and then the previous ones were 13 and 12 still, right? They never go away until I chose them, or perhaps until I stop. So what I have to choose is clearly 4. Right? That's the cheapest of all, so I'm choosing 4. Okay, so here is DG, that is 4. And now, so what we have to do now is choose the next one. What's the best thing we can do? Well, we have 2 choices. We have the 10 here, we have the 12 here. Sorry, can I make this? Sorry, guys, I want to make a point, and so at this point I want to make this 16. Okay, there's a reason I do this, and let me make this 14. Bear with me, I haven't used that word, so it doesn't affect the choices I made, right? I hope you agree with me. Sorry, I took it randomly, but now I'm fixing it a bit so that because now something interesting happens. So here we are with G, right? So what are okay, let's see, what are the options? 13, 12, 8, sorry. I also want to make this 18. I'm sorry, I want to make this expensive for some reason, you'll see. So we have 13, 12, 18, 14, and 16. So what is the lowest cost? 12. So I should take 12. No, because then I create a circuit, right? If I take 12, you see the circuit here, right? So there's one addition I have to do without making a circuit. So that's the one modification I have to make. Otherwise, I won't have a tree. So this is now how it works. You pick the edge of lowest cost, which is adjacent to the previous edges, or adjacent to the previous vertices, perhaps I should say. But you know what I mean here. But there's a constraint without making a circuit. Now, 12 makes a circuit, so I cannot choose that. 13 makes a circuit, so I cannot choose that. So the next available one is 14. Okay, so that is the point that I wanted to make here, and that's why I changed my numbers a little bit. So I'm now have to take 14. I hope everybody is following this, why I cannot take BG nor GI, but it has to be D. dk, and the cost is 14, right? So one more time, the available options to me are this edge that is just colored, but that was not colored yet. There was this edge, there was this edge also, and there was this edge. These were the edges that would connect somehow. So let me undo the previous one. Oh, no, not do it this way. I'm sorry. So one more time, I will go over it. Let me erase this part here so that you can follow again. So I repeat, at this point, what were the edges that I could add because they are adjacent to one of the vertices of the already existing tree? There was this one, there was this one, this one, this one, and this one. These are the only ones that I could do. Of this one, of those, the lowest one was 12, but it makes a circuit. The next lowest one was 13, it makes a circuit. The first one that does not make a circuit is 14, this one, dk, and that's why I have to choose that one. Okay. So what is now next? 13 and 12, I can perhaps already tell myself, okay, they are never going to be, I cannot never take them anymore, okay? So, and for the same reason, you can see here, I can never take 18 because it's going to make a circuit. So if you want, I can rule that out. But, okay, you don't have to do this. This it just means that each time you have to double check that you don't make a circuit. So what are the lowest ones that are available now? So again, 12 and 13 would be available, but they cannot be used. So what is available is 16, 18, and 18. That are the only three. So the lowest one would be 16. So this will be 16. So that's 16. That was DC. And that is cost of 16. Okay. What are, oh, again, I forgot to put a value here. So let me put here the value 3. Okay. So what is available now? The edges that I could add are 3, 5, 18, right? This 18, not this 18 because it makes a circuit. Yeah, I thought I had erased it, but for some reason I didn't. Okay, so not that one because it would make a circuit. It's too big anyway, but it would make a circuit. So of all the lowest one is 3. So I'm taking 3 here. This is CE, and the value is 3. Okay. What are the values now that I can take? 18, but 18 will make now a circuit, so I can already, it's not the lowest one I know, but I can just already say, forget it. It's not, I cannot use it anyway. So I have left with 2 possibilities, 5 and 2, and obviously I'm going to have to take 2. So the 2 here. So this is going to be finally EF, and that is cost 2. Now, do I have a tree? Yes, because everything else would make a circuit, but there's another way of seeing that. How many vertices I have? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 vertices. So I should mention that. The number of vertices is 11. What are the number of edges? Well, here are the edges, so I could even call them the first, the second, the third, the fourth, the fifth, the sixth, the seventh, the eighth, the ninth, and the 10th. And you should do this. I forgot to do this, but it is good to keep listing them, because when you reached one less, remember, for a tree, this is the condition. So once you reach the 10th vertex, you're done. Edge, you're done. That's the nice part of it. So, okay. So what is then the cost? Now that's the cost, right? Now I have to add these numbers, 7, 13, 20, 25, 29, and 59, 62, 64. And so my claim is this is the cheapest way of doing that. Okay, I'll do one more here. Here's one of the book. Let's do this one. So what is the cheapest one here? Well, we have several ones. I can pick any one, so I'm going to pick this one. Okay, so here is, so the first one will be CD. You know what? I'm not going to write it as a thing anymore. I find that very cumbersome. I'm just going to write CD. CD and DC are the same. I'm writing the edge here. So this is the edge. Okay, so how many vertices do we have here? Let's keep track of it. 4, 8, 12 vertices. So I will stop. So here I'll make my table ready already. 4, 5, 6, 7, 8, 9, 10, 11. And once I have the 11th one, I will have a tree. Because this is the magic of these graphs. If a graph has one edge less than a vertex, it is a tree. And this will be even more poignant in the next algorithm. So here you are, edge. What's the cost of this edge? So here comes cost. The cost of that edge was 1. Okay. So the next one, I have now, the adjacent ones are 3, 2, and 5 in cost. 3, 2, and 5. So I'm going to take 2. Okay. So I'm going to take CG. And that is cost 2. Let me mark that. So what are possibilities now? I see 3, 3, 3, and 5. So I have many choices here. I'm going to take, I don't know. Let's take this 3 here. Just to show you that you can really take whatever you want. CB. So CB, so that has value 3. Now I have a cost of 1 available, namely at B. So that's the lowest one. I don't have to think here. So I'm going to take this one, BF. So this is BF, and this is cost 1. What are things now? I see 3s and I see 5s. I see a 2, right? I don't see a 1, so the next best thing I can do is a 2. Let's take the 2. All right, there is 2. So this is AB. That has value 2. What's available now? I see a 3 there, another 3, a 4, a 3, a 5. So let's see here. We have this 3. We have this 4. We have this 3. Oh, no, there's this 2 here. Good thing I checked it here. There's a 2 here, FJ. FJ, there's value 2. Okay, so let's see what we have now. There's a lot of them, so that makes it sometimes this Prim's algorithm works nice, but you'll see the next one is actually better in some sense. So this one, that's a choice. A 3. There's a 4 here. There's a 3 here. There's a 3 there. There's a 3 there. There's a 4 here. There's a 3 there, and there's a 5 here. So I hear 3 to be the lowest one. Now there's one I cannot take anymore, this one. So I'm going to erase that one, scratch it out. You cannot use that one because it forms a circuit. But any other 3 I can use. Any other edge of strength or cost 3 I can use. I'm going to take this one. So again, just to show you that you don't have to continue where you were. I just pick whatever I want. It doesn't matter where you were. Of course, you get different trees by doing different choices. So what are the options now? Well, I basically have actually eliminated this as a possibility. Sorry, I should have done this in red, right? Because it will make a circuit. But I have another 3 that have added, basically, that has been added to the list. So 3, 3, 3, 3. I can use one of the 3s. I'm going to jump. Again, as I said, it really doesn't matter what you do. So I'm going to take this one. AE. Oh, that should have been black. AE, that's value 3. Okay, so that one added as a possibility a 4 and a 4, although this 4 is no longer viable. So we have... well, let's see what we have. We have a 4 here. This one has a 3 here, a 3 here. There's a 4 here. There's a 3 here. So it has to be one of the 3s. I'm going to take this one. So that is JK, and that has value 3. Okay, now it's clear what the next one is because there's only one left, and I'm going to take this one, KL, right? So KL. So that is 1. So now I have 1 more to choose. And you see they're all either 3 and 4. So let's see what is the lowest. Well, let's see what is ruled out. I cannot take this one anymore because it will actually form a circuit. It's a little bit longer circuit, but it will form a circuit. I cannot take this one because that also will form a circuit. So that is also ruled out. So what is available is actually the 2 corner ones here. And the lowest one, of course, is 3. So I'm going to pick that one. There we are. So that is IJ, and that has value 3. And so the cost is 3, 6, 7, 9, 11, 20, 24. Let me double check here. I didn't make any mistakes because I took this from the book. So yes, okay. Now, as you see, this algorithm allows for a lot of freedom, and therefore you're going to have different trees. And notice that these are not rooted trees. This is something... The next step, if you want to, you can now choose a root and make it into a rooted tree. But that is not necessary in this algorithm. Okay? So, that's the first algorithm. And the second algorithm is called Kruskal's algorithm. And he was a New Yorker. So you might like that. Kruskal's algorithm. And in some sense, I find it even more elegant because this one is even, it seems like you're doing even less. So I'm going to tell you what it is that you do. Where is it here? So what we're going to do is, again, pick edge of minimum cost. Wait. Okay. Okay. Now we know that we cannot make a circuit, so I'm going to already add that without making a circuit. And what else? Nothing else. I'm just picking edges of minimum cost without making a circuit. This is weird, right? Because now I'm not building you'll see what happens. Let's do this on this previous example, which unfortunately is so much. So remember, the cost was 64 here. So we found that the minimum cost was 64 when we used Prim's algorithm. But I'm going to erase now all this thing. So okay, I'm going to actually erase this part. Because the idea is still going to be the same. I'm going to start adding edges. How many? Well, 10, because then I know I have a tree. And here I'm going to write the cost. So the principle is exactly the same, except that I weaken somehow my choice. And this should come out to 64. So let's leave the 64 there. But now I have to get rid, and that is always the tricky part, of the color schemes without getting rid of the numbers. Okay. Let's get rid of this. Also get rid of that and that. This one, this one, this one, this one, this one, this one. It was not that bad. Okay. So, Kruskal's algorithm, let me move it up so I don't need Prim anymore. Prim, you have served your purpose. You're going to do the other guy. Okay, here we go. So I'll move them up. Okay, and then this little line that came with it, that has to go. No, so I lost the line here. I lost the line there. Okay. So remember, 64 that's how it has to add up. So I left that number there. But of course, when you do this for the first time, you wouldn't know that. But we have done this already in a different way. I just want to show that it comes out, the value is the same that you're going to get. Okay, so pick edge of minimum cost. Okay, let's do the same one that I picked last time. I think pick A, B. So I could have, I'm going to write them again like this, the cost 2. Pick edge of minimum cost without circuit. Okay, the minimum cost one, the next one is 2. There's another one, 2 here, so I'm going to pick this one. Notice what happens now. This is where you might start, what are you doing, Professor? This is never going to be a tree. Look, they are too far away. They're not going to connect. Patient, my friends, patient. So here we go. So we do EF2. Pick the one with lowest cost. I see a 3. Anybody else see something else? Well, you can yell and shout at me, but I won't hear you, so I'm going to pick the 3. So that is CE3. Pick the one of next. There's a 4, there's a 5, there's another 5, there's a 6, and a 4. So the 4 is the lowest one, so I'm going to pick 4. That is DG. DG, that has cost 4. What's next? Well, so now we have to pick one of the 5s. And here's the first time that we have to make a decision here. We cannot pick this 5 because this would violate this condition here without making a circuit. Notice that these things are far from even paths. They are just, from the moment, edges. I mean, they are what we would call a non-connected graph, right? They form, well, at the moment, but I'm actually building, therefore, remember the fancy word, is a forest. Each of these are trees because I'm never going to make a circuit. So everything that I paint is always going to be a tree, but they're very short trees and there are many of them. So I'm building a forest. That's the difference between the Prim algorithm, which builds a real tree, And that might have its advantage, because it might be that while you're doing this, you want to have already a tree. So you want to go ahead while the rest is being calculating. Whereas this one says, okay, you have to wait until I've done. Otherwise, you don't know how things will work. Okay, so keep going. So we have to rule out now 5. So I'm going to make that sure that I never pick this 5 anymore. But the 2 other 5s I can use, and I'll take, doesn't matter, I'm going to take this 5. Okay, so this is dj. So dj, and it has value 5. There's another 5, okay, see, waiting and not picking it, well, because you have to pick the lowest ones, it's going to come, unless it makes a circuit. So a h, and that is 5. So all the 5s are done, because that 5, the one that I scratched out here, forms a circuit. So let's look at value 6. There's only one 6, so we can take it because it won't make a circuit. So hi, oops, hi has value 6. So for a forest with 3 trees. Okay, next one, 7. I see 7, right? That's the only value I see. Anybody sees? No, 7. Okay, and that's okay. You say, oh, wait. Is that not a circuit, Professor? Because you connect. Well, these things were not connected yet. So if you do 2 unconnected things, it can never be a circuit, right? Because there is no other way to go. So I can take this one, hj. So hj, that is 7, and 2 more to go. Okay, the values are now 14, 13, no, 12, 13, 14, 16, and 18. So 12. What about 12? 12 I cannot pick, because 12 will form a circuit. You see that? Right, the circuit, this would be the circuit, right? It's you have to see it a little bit, but it's the circuit. For the same reason, I cannot pick 13. That was a bit similar. Now, we were kind of getting into the previous situation, but from a different, we approach it from a different way. So 12 and 13 are out, so we have now 14, 16, and 18s left. I'm going to have to pick the 14, because that doesn't form a circuit, so that is still in my options. So dk 14, and then finally 16, 18, or 18. Well, this 18 I cannot take because it will form a circuit, but the other 18 I could take, but there is a lower one, 16, and that does not form a circuit because I'm now connecting this. This one is disconnected from that, so I don't have to think even. This will never be a circuit. As I said, it's sometimes hard to recognize circuits, so it's not as obvious as it sounds, because if it's a huge graph, it's very hard to sometimes see whether it is a circuit or not. But, okay, so this is that, and so we have now DC, this is 16, and now hopefully it comes up. Notice that they are now actually ordered. That's an advantage of Kruskal's algorithm. So this is 30, 37, 43, 43, 53, 57, 60, 64. Yes. Okay, and let's do this the same here and see what happens. And that's everything I'm going to do for today. So this, and so the homeworks will be with this. Okay. In the homeworks, I will also here what we are doing in either case is trying to minimize the cost. But sometimes it's the opposite. You want to have as much as possible, right? It might be that you collect. You get rewards or something like that. I don't know how you can visualize or phrase this, and you do exactly the same thing, replacing minimum by maximum. Okay, so keep that in mind for the homeworks. So okay, here we go. So I'm erasing these guys. Why is it not erasing? Okay. So by the way, so notice that here the costs were not in order, right? There were this one here of cost 1 came very late, and this is not what is going to happen in Kruskal. So okay, here we start, and to me I find it easier to work with. Pick one. Well, pick the one of lowest, which is 1. That's the same as before. Now there's still ones, so let's pick them. Here's one, BF, and there's another one, KL. So these ones are now in there. So this is really greedy, right? I pay as little as possible. But the price is at the moment you're just a forest. Now pick 2s. Okay, I pick this 2. I'm just going to go as I see them. And that is AB. There's another two I can pick. Yeah, the one here below. I'm gonna pick this one, fj. Is there another two? Oh no. Oh no, no. There it is. I thought I saw one here. cg. What is this? cg also two. Now I have to start taking about the trees. Okay, I'm gonna take this tree. I see this tree, so I'm taking it. AE. Another tree. Yeah, the one here below. Okay, let's take this one. IJ. That's also three. Oh, there are three trees I can take here. I'm taking the bottom one. I don't know why. I like the bottom one. Am I making a... I have to worry about this. I'm going to make a circuit? No, because you're connecting two non-connected graphs. So that can never make a circuit. So at the moment, still I don't have to think here. So it's only... So what I'm trying to say is, the only time that you possibly could make a circuit is if you connect. So what I'm doing here, notice that I'm doing... sorry, let me do it again. What I'm doing is connecting a vertex that is already on the forest, in the forest that I have. These two vertices are not connected. They're both in the forest, but they are belonging to different trees, so they cannot make a circuit. Okay? When I add, for instance, if I would add this guy, I don't have to worry at all because I'm connecting something new. That can never be a circuit, right? Okay. So I added this one. JK, did I write him already? No, I didn't write him. JK, that is 3. What else? 3. Well, the next one, I can take this one. I'm going to take the top one. Oh, you say, but you're going to make a circuit? No, because I'm connecting again two trees. At the moment, before I did this, I had one big tree on the left and a small little guy on the right? And so now make this in one big Christmas tree. So that is BC. BC, that is 3. And now another 3 left in my tree. There are two choices, and actually either choice is valid here. So I'm gonna, I don't know which one to take, so I'm taking this one because I'm connecting something new, so it never forms a circuit. So GH and 3. So let's count. We have 1, 2, 3, 4, 5, 15, 21, 24. So again, it checks out. Okay, so this is the story of minimum spanning trees. It's rather cute and it's not so hard, and I think I will do one more quiz on this, and that probably will be our last quiz. Okay.